what you see before you is an awkward elevator moment. Why? Because elevators are an example of rectilinear motion, which is what our second objective is all about. You will be able to find the instantaneous velocity of an object in rectilinear motion. And as far as the AB calculus course is concerned, it's the only kind of motion that we consider. In BC calculus, towards the end of the year, we'll also do something called curvilinear motion. So what is rectilinear motion? Rectilinear motion is just movement along a straight line with respect to an origin point. We are bound to some sort of axis, like this one could be the x-axis. We're just moving left or right. You can see right here in the word, the root word is line, linear, right? We're moving on a line. Or we can move up and down, sort of like on the y-axis here. And if we're moving up and down, movement upwards is in the positive direction. That makes sense if I relate it to the y-axis. And then movement downwards, is in the negative direction. Likewise, if I'm bound to a horizontal axis, like the x-axis, if I'm moving towards the right, that's the positive direction, and movement towards the left is the negative direction. So now let's talk about the position of a particular particle or an object bound by one of these axes. And we're going to denote its position with a position function. The position of an object experiencing rectilinear motion is given by a position function. S is equal to f of t. S is usually the name of the function that calculus gives to its position function. And I believe in physics, you often use x for the name of its function. And notice that it is a function of time, where s is the distance from the origin point at some time t. And we can see a diagram here. We don't have an x and a y axis. We just have a single axis where our particle is moving backwards and forwards on it. So let's say that I have an ordered pair here. S of 0 is equal to -5. Let's interpret what this means in the context of the position function. Well, 0, that's on the inside here, that's the time. So this is at time t equals 0 seconds perhaps, and the -5 here is its position. It means that it is 5 units to the left of the origin point. Okay, so one of the things that we often talk about in terms of particle motion is its velocity. And soon we'll also talk about its acceleration. But right now, let's talk about the average velocity. Average velocity is just simply the change in position over some sort of time interval. So, for example, we have our particle. It starts at this position, this particular position. It will be at f of a at time a. And then we want to know, let's say after some time period has expired, a plus h, it has moved to a new position, f of a plus h. And we want to know what was the average velocity of that particle. And it is just simply the distance that it traveled over the time it took to travel there, right? And we want to know, hey, let's just go ahead and find, for this particular instance, let's find this average velocity. Man, I wonder what it's going to be. I can't even imagine. All right, so we want, for average velocity here, average velocity, it is basically the change in position. Come on. Over the change in time. So let's use the quantities that are given in this picture here. So the change in position here, I'm going to start at this f of a plus h and end here at f of a. So there's my change in position. So, delta y, except for they're not y coordinates, over some change in time. So my change in time here, going in the same order, this a plus h minus a. And well, look at that. The a's cancel, and man, that looks really familiar. That just looks like the difference quotient, the slope of a secant line that we've been working with all along. Because you know why? That's exactly what it is. Okay, so average velocity, change in position over change in time. in terms of the position function, that is f of a plus h minus f of a over h. Yeah, that's the change in time. Okay, so that's average velocity, and this is the only thing that you could have calculated prior to calculus. Now what we can do is that we can make this h as small as possible. We can see what happens when h approaches 0, and that becomes the instantaneous velocity. Oh yeah, it did tell me that we just found a slope of a secant line. So as h approaches 0, the average velocity approaches the instantaneous velocity. And this is the way we calculate it, based on our limit. I'm going to take the limit as h goes to 0 of that average velocity. So v of a means the velocity at time a. The velocity at time a, instantaneous velocity, is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. It's the exact same thing that we were doing in the first objective, but we're putting it within the context of rectilinear motion. All right, so in the next video, we'll actually put this new formula into practice.